it just opened up the world that could become. That was our first electronic computer, and it did open up anybody who wanted to do fairly difficult or elaborate or lengthy calculations.
I knew about computers before that because I was a science fiction fan. And in 1950, science fiction was writing about giant brains.
Back in the day, they were called, the electronic brain.
Even when we talk about its early days, we often use CSIR because it's less clunky than CSIR Mark1.
Well, CSIR occupies something like 30 square metres.
It was a row of grey cabinets.
It had its own power supply.
And it ran, of course, using very high voltages compared with today's computers.
It had a processor consisting of 3 very large cabinets.
It used a colossal number of 6SN7s.
Here we can see some of the vacuum tubes inside the computer. There were over 2,000 vacuum tubes in the computer, which were, of course, the technology at the time because this computer was built before transistors were available.
There were valves being made in Australia, so it's entirely possible that everything was made in Australia from raw materials.
Had its own air conditioning system with air being blown through it to keep it cool.
The transformers were all wound in Australia.
Across the front of the cabinets, it had neons which told you the contents of critical registers.
There were lights flashing which could give an indication of the progress of the computer. There was a control console where an operator would have to intervene in the program at certain definite times to control the progress.
And the switches could be used to load information into memory, to tell the program to run, to say start, and also to step through. That was a common feature of a lot of early computers, the single step button to step through a program.
It's a little bit of an art, but they said that the person had the ability of a concert pianist.
The technology in the United States was generally punch cards, Hollerith cards, and that was the technology used for CSIR Mark1. They found it unreliable, the devices they had, probably secondhand. We still have pictures of those devices with their metal Queen Anne legs, but they gave up on them and they made instead paper tape readers and paper tape punchers, which used a unique form of paper tape. It was really like a Hollerith card that went on and on and on.
Its main medium for accepting programs and data is paper tape of 2 kinds. One, a wide kind with 12 channels, frequently used for recording programs, and one of 5 channels, identical with paper tape used in common telegraphic equipment.
This is the console. The programs were fed in by this 12-channel paper tape, fed through a reader here. The operator sat and operated this set of switches which controlled the operation of the computer and could see what was going on in these cathode ray tubes, like small TV tubes, which were along the front of the console.
There were 6 of them on the console. There were various meters with needles, and if it broke down, they could then work out where the computer program had crashed.
It was a serial machine, so the pulses which formed the bits in the main arithmetic registers were proceeded serially in time.
The highest clock speed in the computer was about 1 megahertz, but then that was much slowed down by the fact that it was a serial machine. So bits went one after another. So the ultimate execution speed of the machine normally stayed as 1,000 operations a second, 0.001 megahertz these days.
This is the memory of CSIR. Building a memory for an early computer was always difficult. This memory was built using mercury delay lines. These are long tubes which hold mercury, and the electrical signals, the pulses, are sent from one end to the other through the mercury as sound waves, picked up at the other end, and then amplified and sent around again. This meant that one could store digital pulses, a train of digital pulses circulating round and round in the mercury delay line. There were 24 of these lines, each holding 32 words, and so CSIR at its maximum had 768 20-bit words, all held in this mercury delay line store.
Storage capacity was designed with a 10-bit address, which meant that you could in principle address 1024. For some reason, it had been implemented at 768, 20-bit words, and it was never shifted from that. And the person who came into play here was Reg Ryan, who was a young engineer. He thought up a way of interleaving the pulses in the mercury delay line, so he doubled the capacity.
It had input and output devices.
It had a backing store, which was in various implementations, been tried in Sydney, a sort of coffee drum type thing.
The first magnetic storage system on the computer was this one. This was a drum where the drum rotates and the digits are stored on the drum with read and write heads here. This turned out to not be terribly satisfactory, and so this larger disc was built where the magnetic recording is done on the side of the platter, rather like a disc today. These are the leads going to the read and write heads.
That held another 1,000 words, and later on the other side of it was implemented, and that much later in the piece, for another 1,000.
This was driven with an electric motor and V-belts on this pulley here, and the way you started it up was to start the motor and then press the screwdriver on the V-belt and bring the disc up to speed.
The speaker, it was a roller speaker. It could well have been manufactured here. Many of the early machines used bells as an indicator that something had finished, or they would trip a relay that would trigger an oscillator. Turn an oscillator on and go bzzz, and you knew that it had finished. And so having a programmable hooter on CSIRAC, I think that was probably the cheapest and simplest option, and nobody at the time cared what it sounded like. It's just like, yep, we'll put a speaker there, we'll make it a destination on the bus, it will make a noise of some kind, we'll be happy.
And at the end of the process, apparently a large hooter would go off to say, we're finished.
Somebody had to turn it on, warm it up, do all these margin checks, run a test program. You had to put in the first bootstrap, which you did with keys, which fed in the first little loading tape into the paper tape reader.
There was no operating system with CSIRAC. You first of all entered a routine called the primary routine, which then read in what was known as the control routine, and the primary and control together then enabled the rest of the program to be read in.
Which then conditioned the machine then to take your tape, and as you sat there you watched the memory filling with all the bits. You basically have set start instruction, hit the go button and kept your fingers crossed.
Programming of the computer such as CSIRAC in the initial stages had to be done by writing your program directly in machine code, using mnemonics for the instructions that were well developed.
You had a coding pad and wrote the symbolic code on a piece of paper, in effect. And we had relative addressing, so it was a nice programming environment. And then you had to go into CSIRAC and punch it out on one of these machines. It was just an encoding punch. It had a symbolic keyboard, so you punched it in the symbols that you were familiar with, produced a 12-hole tape. You had to copy a bootstrap onto the front of that tape, and then you read that into the reader, and that stored the program in the machine, and then you told the machine to go ahead and do it.
The binary code for CSIRAC was a source and a destination. 32 sources, 32 destinations, 1,024 commands in all. If you were creative, you could do wonderful things with the coding. You could turn a very difficult long code into a few short commands.
It was a source destination system, which it was easy to think about and nice to use. I liked it. I thought it was excellent.
The programmers used this simple instruction set to build up a software library.
The program library, if you want to do floating point or something like that, you took a tape and you took it out of the library and copied it in, as it were, into your program.
Divide was a routine which you had to copy onto your program tape if you wanted to divide two numbers together. And the same with the trigonometric functions and the input-output, the print routines and the routines for inputting numbers into your data into the machine. Well, these were all library programs, and there was a library of 12-hole paper tape.
And literally a pigeonholes of boxes with punch paper tape in. You go, oh, I want the library that would do this, and you could load that in, etc.
particularly in those days, you reused as much as you could of things that other people had done.
And of course, each of these had been very well worked over to actually optimise time and space. So you could actually build quite a reasonable program by splicing together these library programs.
Then it must have been one of the first software libraries available. Yeah, absolutely.
CSIR, to me, as a prototype, was essentially for the development and study of programming.
It had quite a lot of functions. It helped produce calculations for the Snowy Mountains scheme.
Well, the Snowy Mountains hydroelectric people, of course, came. Others were from various divisions of CSIRO, and some university people.
One of Australia's unsung heroes is Jeff Hill, and he was Australia's first software engineer. He was a mathematician who wrote software for CSIR.
One of the earliest hackers, if you like.
Fairly early in the project, as far as I can tell, in Sydney, Jeff came on board.
As programmers, Hill and I were interested in the programming, as distinct from the actual task being performed.
It was applied to a lot of work.
It was running astronomical calculations for physicists and astronomers, etc.
They were also interested in the question of what the hell was rain and how did it work. It was used to do rain calculations on the raindrops and things like that.
Trevor was doing interesting simulation work on raindrops. And this is fluid dynamics, that was very early work on the computer. He published a paper in 1955, which is very early for simulating raindrops.
Didn't take long, of course, typical computing, for people to start to think of other uses for it.
I don't know whether it was 52, maybe later. I think there was a game of NIM which people could play.
The playing of what might be called music.
This is thanks to the efforts of Jeff Hill in Sydney, who was the one who wrote the first music.
The first time it played music publicly was at Australia's first computing conference in Sydney. Currently, it looks like it was the world's first computer to play music. It was the fourth computer in the world. Roy Munsey remembered hearing it when he started, and that dates it to a good 6 months before that conference.
I do remember hearing it.
Well, they weren't major symphonies.
It started out with scales. Colonel Bogey's March was the first thing, which was a very popular tune of its day, you know, da, 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 da.
Something called In Cellar Cool, and I believe Happy Birthday. But they really exercises in seeing whether you could program the computer to generate music.
And Jeff Hill came from a musical family, which is important in the story of the music of CSIR. And so they would put a blurt at the end of a program, which is just send some pulses. Remember, CSIR is a serial machine. You'd send some pulses to a speaker, and the speaker would go like that. And you go, oh, okay, program's finished. But Jeff Hill was a mathematician, and he would realise that, okay, if I could send these pulses at a regular time, I will get a steady pitch. Now, that sounds like an easy task given today's machines. However, when you have a machine with 1,000 hertz major clock cycle, each memory access takes a different amount of time. Sending a regular pulse to a speaker becomes quite a programming feat. He managed to do it.
Quite a remarkable achievement, and intellectually very difficult, very, very complicated.
Initially, it was a programming challenge because it was such a challenge on CSIR. You need to know the machine extremely well, how to send the pulses to the speaker at a regular period.
The tones were not pure tones. They did their best. The music programmers did their best to produce pure tones, but it wasn't always possible, and some of the tones were a bit discordant.
I actually found a copy of the instructions for the music program and found such gems as, if transposition beyond these limits is attempted, the computer will be asked for notes that are not in its repertoire and will go berserk, which is a beautiful way of putting things, I think.
Jeff Hill had a sense of humour, so when CSIR's memory was expanded, he programmed the tune Thanks for the Memories.
So the first Australian Computer Conference was held in Sydney in 1951.
It was publicly exhibited in 1951 at the first computer conference.
Which Hartree came out and was the main speaker.
The CSIR project was a feature of it.
They were able to demonstrate to people the potential of digital computing.
People walked out of the conference, slack-jawed. This thing plays music as well.
To have it amuse them with a piece of music was something to perhaps break down the barrier of a machine.
Certainly CSIR got plenty of exposure and must have been quite a remarkable thing to find in
in the bottom end of the world in 1951.
There was a potential with CSIR, I don't know if it ever happened, that people could play a bit of music at the end of a program.
The music was quite regularly played to people just to show what could be done.
Bonnie Banks was programmed for the then Prime Minister Sir Robert Menzies to try and popularise the machine with him to keep the project going.
Development thereafter was really as a prototype machine. There was nothing else like it in the neighbourhood. It was a prototype in the sense that CSIR, which was built at the University of Sydney during the mid-50s, was not a prototype. It was more or less a copy of a working system in the University of Illinois.
You know, there's always competition for money.
There was a review of the CSIR project within the CSIR, and they decided that private enterprise would be better to drive computing.
They put it out to tender to 3 different Australian companies, probably AWA, Philips and STC, to see whether they could actually take this on and manufacture it.
No one was interested in putting in the money to commercialise CSIR.
Radiophysics towards the 50s became one of the world's prime centres in radio astronomy, and more resources, I think, were devoted more and more to radio astronomy, which was quite justifiable.
But also there was also a new person at the Sydney University, Harry Nessel, who came in with the idea that it was a bit old-fashioned now and they could get a nice new version of a computer, a more modern computer.
Radiophysics had decided to give up that project, and that was why the computer came to Melbourne.
The decision by the Division of Radiophysics, or might have been more by the executive of CSIR, to close down the CSIR project and give the machine away. I have considered during most of my life that was a disaster. It was a very short-sighted decision, and that a great opportunity was lost at that time.
Bowen and Pearcey, who were the 2 senior figures in the radiophysics division of CSIRO, which had supported the development of the CSIR MARK1 computer, with Trevor Pearcey in charge of designing it, really believed that the computer would be better off in the longer term going out to a different environment.
The development of CSIR became more of a sideline in radiophysics. Resources became rather difficult to achieve to complete CSIR.
We've moved on from this stage in computing. We've gone to another stage, and you've missed the boat.
I suppose it was a long time before people thought of the computer as being more than simply a calculating machine.
So they looked around for what the alternative options for the computer would be. First, there was talk about sending it to the Aeronautical Research Laboratories in Melbourne down at Fisherman's Bend, where they would clearly use it for their own computing purposes. But I think both Bowen and Pearcey really wanted the computer to go into a situation where it could further computing in Australia, and that really suggested a university environment where diverse users could start to get training in this new field.
The CSIR project at the University of Sydney Radiophysics was shut down.
CSIR Mark1 was dismantled in Sydney, carefully placed on a flatbed truck covered in a tarpaulin, and then trucked to Melbourne to have a new life as CSIR,
where it was used to set up Australia's first computing department at a university.
In a sense, we'd inherited Trevor's baby,
where it provided the training ground for the first generation of computer programmers.
CSIR became CSIRO, and so they renamed it the CSIR. So it was CSIR Automatic Computer. It's been known as CSIR ever since.
He was very disappointed when the CSIRO decided to shut down the program. He felt that they were ready to move to the next stage, Mark 2, rather than shut it down and give it away.
I understand a little more why they made the decision, because they had great trouble in finding the right sort of leadership for the project. Pearcey was too much of a dreamer, and the project had rabbited on for a long time. It was never quite made reliable enough to make it appear to them to be really useful. Now that changed when it got to Melbourne, and it changed because the management changed. There was some proper support put in. It wasn't left to a couple of research scientists to do as a research project. It was set up to be a tool to use, and there was an engineering approach to it. with all due respect to the people of radiophysics, I don't think those people of radiophysics had the proper resources and support that they should have had. Now, they may have antagonised people. I've heard stories of personality problems at radiophysics and so on, but I wasn't there. I don't know.
I was very disillusioned, I'm afraid, and spent the next 18 months in the UK at Great Malvern with a fast machine of the same vintage, parallel machine, vacuum tube generation, known as TRIAC.
So he was disappointed. I mean, he devoted his life to that computer.